Hello everybody. In the last session we had discussed about electromagnetism towards the end of the session, and we carry it on in this session also to understand the basics of the transformer. So today's topic would be the basic principle of the transformer. Transformer basics. Transformer, as we said, is an electromagnetic device. There is part of the energy which is part of the portion of the transformer which is associated with the electric domain, and there is another part of the transformer which is associated with the magnetic domain. Energy flows across the domain from the electric to the magnetic, magnetic to back again the electric. There is absolutely no connection between one port of the transformer and the other port of the transformer. The connection or the interconnection energy wise is only through the magnetic domain. So we saw that a transformer consists of a core, and on the core we have some windings. So we have two windings, one for the primary, and another for the secondary. So this is the transformer winding. So we have the primary port or the primary side port, which has its two variables, the potential variable, the voltage E primary and the current I primary. Then on the secondary side we have, of course, the E secondary, the voltage across the secondary terminals, and the current through the secondary winding if there is a load connected. If there is no load connected, Is is equal to 0. Now you see that the primary side electric circuit, secondary side electric circuit, whatever is going to be there, is not physically connected. The only transfer of energy can occur is through this magnetic domain, the core here, the core. And we saw here that primarily we will be using Faraday's law of electromagnetism, which is voltage V across the coil, induced across the coil, will be equal to N, the winding number of windings in the coil, into d phi by dt. This is called the Faraday's law of electromagnetism. This law is the one which is going to be extensively used to derive various other relationships. Now, let us take this figure here So, I have marked this figure. I am going to copy that, go to the next page, and we will paste that and then use this figure. Now, if you see here, let us say that there is some voltage which is going to be applied here. So, a voltage is applied here, EP or V primary. This voltage source, once it is applied, is going to cause a current IP to flow through the primary coils. So, once a current IP is flowing through the primary coil, there is going to be a rate of change of flux induced within the core. That is, EP will be, let me say that there are N1 or NP number of turns connected turns on the primary coil and NS number of turns on the secondary coil. So, EP will be NP d phi by dt. So, the voltage EP which is across the coil, which is applied from the source directly, as there is no other impedances, that should also be the voltage across the coil by Kirchhoff's voltage law, and that is driving a current IP. Now, this IP is setting up a magnetic field within the core, and the field, the flux inside the core is going to have a rate similar to the applied voltage. So, if the applied voltage is having a particular frequency, the frequency at which the flux is going to change will also be the same. So, this d phi by dt is the rate of change of flux within the core. So, there will be a flux which will be set up in the core. So, there will be a flux which is set up in the core, and that has a d phi by dt. That is what is causing the induction of the voltage across the coil. Now, the same flux is linking the secondary also. So, therefore, if we look at the secondary coil, ES will be NS d phi by dt. That is, there is another coil here, NS, the same flux flowing through the coil. So, NS d phi by dt is going to cause a voltage ES to be induced across the secondary coil. All this by Faraday's law, isn't it? Both of these are by Faraday's law. Faraday's law. Now, E secondary by E primary, that is the voltage across the secondary divided by the voltage across the primary of the coil, that is the ratio of the secondary voltage across the secondary port to the voltage across the primary port, is equal to, using these two terms, you have NS by NP, because d phi by dt is the same for both the coils, because it is the same flux which is linking both the coils. So, this means that E secondary is NS by NP into E primary. So, if there is a primary voltage EP applied across the primary port, then if Ns is the secondary number of turns, Np is the primary number of turns, then the secondary voltage induced across the secondary port Es will be the ratio of the turns Ns by Np into Ep. This is one of the major equations for the transformer operation. The primary, on the primary side here, okay, let me again use that. Now, the primary here is containing Np number of turns and is Ns number of turns. Now, the power at the primary is Ep Ip. The power at the secondary port is Es Is. Now, we know that this transformer is lossless. There is no loss in the transformer, in an ideal transformer. Of course, the practical transformer will have some losses, we will discuss about that later. But let us say an ideal transformer, there is absolutely no loss, no accumulation of energy. So, whatever energy comes into this port will get transferred to the other port. So, which means this should be equal to this, in which case we can obtain the relationship between Ip and Is. We know that Es is equal to Ns by Np into Ep. So, if you substitute for Es here, we get Ep into Ip will be Ns by Np into Ep into Is. So, this is Es. So, we have Ep on both the sides, we remove that, and this results in Ip by Is, which is equal to Ns by Np, or Ip is just equal to Ns by Np into Is. This is the other relation, that is the relation for the other variable, the kinetic variable. So, summarizing, we have these two important relationships, Es by Ep, which is equal to Ns by Np. This is for the potential variable. Variables of the ports, two ports. Then Ip by Is equals Ns by Np. This is for kinetic variables of the port, or you could say this is the effort variables, the flow variables of the ports. Note here the inverse proportionality, Es by Ep, which is equal to Ns by Np. Es is proportional to the proportionality to the turns, number of turns. The current is inversely proportional to the turns Ip and Np, Is and Ns, so that the energy conservation is obeyed. so that the power at the primary and the power at the secondary under ideal conditions will be the same. Now, to understand a bit more further about the transformer and the magnetics, there is one more law that one needs to understand about. Let us say there is a conductor, Now this conductor is carrying a current. So this conductor is carrying a current I. So if this conductor is carrying a current I through it, then it is going to generate a magnetic field around that. So there will be a magnetic field around this conductor. With some direction, and this is called, this law is called the Ampere's law. What does Ampere's law state? If there is a current carrying conductor, then that will create a magnetic field around the conductor as shown here of some intensity H. H is the magnetic field intensity. This is in amps per meter. In other words, the converse is also true, meaning if there is a magnetic field intensity around a conductor, then there will exist a current which will flow through the conductor. So the converse of the Ampere's law is also true. If there is a current through the conductor, it will generate a magnetic field intensity of H around the conductor. If there is a magnetic field intensity of H around the conductor, then there will exist a current which will be flowing through the conductor. So both the converse and the Ampere's law is valid. Now, to get an idea of the direction, we use the thumb to point let me draw this. Okay, so we have the right hand, we have the thumb, so is the wrist. Now let the thumb point in the direction of the current. Assume that a current is flowing out of the picture towards the camera. the thumb is pointing in the direction of the current and the fingers are folded as shown here along the flux lines. You see the flux lines which are orthogonal in an orthogonal plane to which the current is flowing. The fingers point in the direction in which the flux is going to flow. So, as the fingers are pointing here for a current flowing in this direction, you will see the anti-clockwise direction of the field lines. This is the right hand rule. Now, mathematically we can state the Ampere's law as integral of H dot dl 0 to Lm, which is the magnetic path length, is equal to mmf or amp turns N into I. This is in ampere turns. This is the units. This is the mathematical statement of Ampere's law. What does it mean? Again, coming back to the conductor, we have this conductor and through the conductor we are going to pass a current I, and let us say I have number of conductors. Number of such similar conductors so on. Each having the same current I, and let that number be N. You have N such conductors. So, about these N conductors there is going to be a flux, a magnetic field, and that magnetic field H is also dependent on the path length, the magnetic path length, that is Lm. So, if you integrate H around the path, then that is going to give you N into I, ampere turns, or the magnetomotive force. If N is 1, then integral of the magnetic field intensity around the path length is going to give you the current I. Now, this is the implication of the Ampere's law. You have a current I, and if there are N such conductors, all carrying the same current, then Ni would be the magnetomotive force which is going to drive the flux in the magnetic material around the conductor. So, this means that if you have a coil, let us have a coil, let me draw the coil. So this is like that, and the current goes through like this, goes through the coil, and then comes out here, a current I. Now if you take this portion, let us say this coil portion here, you will see that there are this portion here, you will see that there are two conductors carrying current I, which means there will be a magnetic field like this. So if there are two, or if there is n such conductors, each carrying current I in this coil, and that is causing a field of intensity H being created, and on integrating this H around this magnetic path length, Lm will give you Ni, depending upon how many turns you have put. So this is the principle in which Ni, that the magnetomotive force, is created. There is one more term that you need to be familiar with, which is the flux density. And that is having a symbol B. So from the Ampere's law, we saw that 0 to Lm H dot dl is equal to Ni, which is the MMF for the magnetomotive force. If H were uniform throughout the path length, then H integral of path length will be Ni, or the MMF, or H into Lm is equal to Ni. The magnetic field intensity H is equal to Ni MMF by the magnetic path length Lm. This is having units of amps per meter. Now as I was saying here, B is the flux density. There is a magnetic flux phi per unit unit area or cross section area of the core, that is cross section area through which the flux is flowing. So if we have the cross section area of the core and flux is flowing in this direction through the core, this cross section area, which is orthogonal to the flow of the flux, is AC. So flux per unit area, this is having units of Tesla. Flux per unit area or Webers per unit area is Tesla. Flux has the unit of Webers. Webers per meter square is Tesla, named after the famous scientist Tesla, who has contributed so B and H. B is flux density, H is the field intensity, which is basically the motive force for generating the flow of flux. How are these two related? Ideally, if we plot B and H, they should be a linear straight line, B and H. This is how it would be for vacuum, a free space. This is flux per unit area. This is MMF Ni by path length. Amps per meter. This is Tesla or Webers per meter square. Now this slope here, delta B, delta H, is mu. Mu is equal to delta B by delta H, and if it is linear, it is B by H. So this means flux density B is equal to mu H. However, the flux in the core is not linearly related to the magnetomotive force as shown in the previous graph. It exhibits a hysteresis nature. Let us say we have a graph, 4-quadrant graph, x and y axis, and let us say the x axis is the H, magnetic field intensity, the y axis is B, which is the flux density, which is equal to phi by AC, and this is equal to Ni by Lm. So in actuality, you will see that, let us say we start with a virgin specimen, a new specimen. As the field intensity increases, as the magnetomotive force increases, the flux in the core will increase. Flux keeps on increasing as you increase the magnetomotive force in the x direction. But you see that it loses its linearity and gradually it starts to saturate. So beyond a particular value of magnetic field intensity, the flux in the core will not increase any further. Then let us bring back the magnetic field intensity towards 0. So as you start bringing it towards 0, you will see that it does not come back along the same path. It exhibits hysteresis. So when the magnetic field intensity is 0, there is some remnant flux which is in the core. So to make that 0, you have to give a coercive force in the negative direction, that is, you have to give a negative flux intensity or negative MMF in the other direction, then the flux is totally removed. So when you start giving H in the negative direction, this continues further, then beyond a particular value, flux does not go any further, it saturates. Then when we bring back the field intensity again the positive direction, this starts again exhibiting the hysteresis. There is a remnant flux when H is 0. To make the flux 0, you have to apply a positive H, and then this will swing in this So, aversion specimen starts with 0 and then from there on it exhibits this kind of a hysteresis curve. So, all magnetic materials will exhibit this kind of a hysteresis curve called the BH loop. So, the magnetomotive force, which is proportional to the magnetic field intensity, is not linearly related to the flux in the core or the flux density B in the core. It is related by this kind of a graph which exhibits hysteresis, and this is called the BH curve or the BH loop. Now, we have few equations here we need to put it down. First one was, you have the field intensity which is Ni by Lm, which is nothing but mmf. mmf is the ampere turns by Lm. Now, the second is the flux density B, which is given by the flux in the core per unit cross section area. Then third, the relationship between B and H in the linear region mu H. So, B is equal to mu H in the linear region. Mu is a constant. However, in a practical core, mu is not constant, as we saw that it exhibits hysteresis. BH curve exhibits hysteresis. Mu is varying from point to point. So, it depends upon the operating point. It is more or less linear close to the 0 operating point. So, these three relations govern the operating principle of the transformer. Now, let us have a look at what happens inside the core of a practical transformer. In a practical transformer, there is going to be some loss. What are the losses in the practical transformer? There are two types of losses in the core of the transformer. The losses in the core of the transformer, one is called the hysteresis loss, the other is called the eddy current loss. Eddy current loss. These are the two losses that occur within the transformer. So, if you take this core material, so there is going to be an input energy here going through into this port. So, EP IP, and then there is going to be ES IS which comes out of the secondary port. But in between, inside in the core, there is one, the hysteresis loss, P H, the eddy current loss PE. Further, there is going to be some finite resistance in the coil of the conductor, and I square R is going to be lost. IP square RP is going to be lost in the primary. IS square RS is going to be lost in the secondary. Now, this occurs in the copper, and that is called the copper loss, PCU. So, what occurs at the secondary ES will be the primary power minus these losses, which would be pH, PE and PCU. So, it will not be exactly same as the primary power what you would get at the secondary side. It would be less by an amount equivalent to the losses which are encountered, like the hysteresis loss, the eddy current losses in the core, called the core losses. These are called the core losses, and the copper loss. So, keep this in mind, that in a practical transformer, the power output is going to be slightly lesser than the power input by an amount equal to the losses, the core losses and the copper loss. And the core losses is composed of two main components, the hysteresis loss and the eddy current loss. Now, let us see what these losses are. So, first let us take up the hysteresis loss. In the core, we saw that the BH curve exhibits a hysteresis curve or the hysteresis loop. It is not linear in nature. And the B, the flux density B, is given by mu H, where mu is not a constant, but it keeps changing based on the operating point. And this is equal to mu H is N I by L M. So, therefore, I is equal to B L M by N mu N. This is one equation. The other equation, so this equation is coming from the Ampere's law. Ampere's law. Another equation as a result of the Faraday's law. We have V is equal to N d phi by dt, which is equal to N. Now, phi is nothing but B AC, isn't it? So, if AC is constant, Bn AC dB by dt. This is the other equation which comes from the Faraday's law. which comes from the Faraday's law. Now, the instantaneous energy delta E, instantaneous energy delta E is voltage into current into time delta t. And this is given by voltage given by the Faraday's law, which is N A C dB by dt, that is for this. Then I is given from the Ampere's law, which is B Lm by mu n, B Lm by mu n into dt. This is equation 1, equation 2. This is the instantaneous energy. This is having a units of joules, instantaneous energy in the core. Now, here AC and Lm, magnetic path length and the cross section area together gives the core volume Vc. This is core volume, and of course we don't directly cancel like that, but it effectively means that we now have N Vc B dB by mu n. So, this n and this n also goes off, and we have a very simple equation Vc B by mu into dP. This is the instantaneous energy. Now, energy d, which is equal to B by mu into dB, is the energy per unit volume. So, in one cycle, that is one cycle, if we go back and have a look at the hysteresis curve, in one cycle, as the flux density B is swung from positive to the negative, positive to the negative, the hysteresis loop is traversed. The hysteresis loop is traversed, and we see here that the energy E is nothing but H dot dB, or integral of dE will give you integral of this, which is the energy per unit volume which is traversed for one cycle, and is traversed for one whole cycle. So, we integrate it for one period 0 to t. Now, what is this? From the BH loop, we have this. So, H is traversing, the H is traversing positive, that is, as B is traversing positive and negative, H is also traversing along this, and an integral of this is going to be basically this area, and that area is going to be lost forever. That energy is going to be lost forever, it is not going to be got back. That is called the hysteresis loss. So, as B is varied, the hysteresis curve is traversed. The integral of H dot dB would mean this area, and this energy is lost forever and it does not go to the output, and therefore, this is called the hysteresis loss. So, therefore, integral of dE is equal to integral of B by mu dB, which is equal to half B square by mu dB, which is equal to half BH dB. Sorry. After integrating, half BH, half BH. Now, the energy including the core volume would be, so hysteresis energy including core volume is given by half, because that was energy per unit volume. This is half BH into VC, the core volume. Now, the power hysteresis loss is the rate of energy, which is divided by the period, one period. So, power is 1 by T EH, which is half BH VC into F. So, this is the hysteresis loss equation. See that the hysteresis loss is directly dependent on the flux density, magnetic field intensity, on the core volume. Larger the core, more the hysteresis loss. And another important thing is the frequency of operation. As the frequency of operation increases, the hysteresis loss is going to increase. This is also in keeping with what we understand, because we are talking of the hysteresis loop. Now, the one traversal of this hysteresis loop means this area is covered, and that amount goes into what is called the hysteresis loss, which is unrecoverable. More number of times, if this is traversed in a second, you are going to have more loss, which is basically what the frequency issue coming up here. Higher the frequency, more number of times this hysteresis loop is going to be traversed in a second, therefore, higher is going to be the loss. Therefore, hysteresis loss is also proportional to the frequency of operation. And then we have the eddy current loss. The eddy current loss. The eddy current loss can be explained easily from our Ampere's law. We have a core. Let me draw a three-dimensional view of this core. Which is like that. This is a three-dimensional view of this core. Now, this core, let me take a cross section. The flux is going through the core in this fashion. So, as the flux is going through this core, of course, that is due to a magnetic field intensity, there is going to be a current loop like that. Because we saw that the converse of the Ampere's law is also true. If there is a current in the conductor, there is a flux around the conductor. If there is a flux around the conductor, there has to be current through the conductor. Now, these currents I are going to produce I square loss in the core material. This causes a loss which is unrecoverable, and that is called the eddy current loss. We will discuss about the eddy current losses and the other aspects of the transformer in the next session. Thank you.